if my slides are visible.
Slide are visible, sir.
All right, thank you. So in this quick session, I'll give you a brief introduction about artificial intelligence. I'm sure our listeners are already aware of that. Then I'll be talking a bit about the biometrics, which is one of the streams of artificial intelligence, and you can say it is kind of subsidiary, which helps in healthcare a lot, although it has its own usage in cybersecurity, in surveillance, in many other domains for providing different security aspects, but it has got a lot of work to do uh, with healthcare as well. And then I'll be taking a couple of test cases, and that I'll be explaining you with the experimental facts and results. And I'll try to cover everything in this short session itself. If at all I find some shortage of time, then I'll be going a bit quickly and might be skipping a few slides. So initially, I think the basic things I can go a bit faster so that I can come to the actual matter that I want to present. Artificial intelligence is a big buzzing term around the world nowadays, and ever since the term has been coined, there are researchers, there are scientists, there are businessmen. They have their very strong opinion, and if you just go through, you'll find they are very much polarized. You see people like Stephen Hawking and Alan Turing, those who are not very convinced with artificial intelligence. At the same time, Elon Musk, Andrew Ng, you will find their terms, their definitions to be on very much on the negative side of AI. It's not like they don't appreciate. They actually work with the AI so much that they fear, they sense the time when they might overcome humanity. Or at the same time, you'll find some very big persons in the domain of robotics, and there are people who are compassionate in AI movement. They support artificial intelligence in a big way, and they believe that there will be a time when artificial intelligence led systems will be doing all the D's, like difficult, demanding, and dangerous, dull. All such tasks will be done by them, and this will give us more time as a human to contact each other, to spend time with each other, and in a way, this will help us to socialize, to give time to each other, and make our life really more beautiful. So, all right, keeping all the discussions and thoughts aside, our takeaway definition for artificial intelligence is to bring this intelligence artificially. We'll cover this term once again in a while. So, technical aspect of the artificial intelligence is to aid human capability and help us make advanced decisions with far-reaching consequences. We also can say that we have a philosophical perspective of artificial intelligence, which will let human life to be more meaningful by when we will be giving more time to each other. If you see where these aspects are available, there is a slight printing mistake over here. So applications of artificial intelligence, it is there everywhere, be it healthcare, automobile, finance, surveillance, social media, entertainment, education. Artificial intelligence is coming in big way. To see artificial intelligence in healthcare and medicine, it's coming with virtual nursing assistant, medical image analysis, AI-assisted medical analysis. So there are so many images, like the images which are taken from CT scan, the images which are taken from X-ray images, and all these images which are taken, there is a huge image processing and computer vision related aspect at which we are getting information out of these images, and we are running our machine learning, deep learning algorithms, and coming up with very different type of inferences. So on one side, if you see, there are so many chemical laboratories and so many different types of tests which are happening at chemical levels. At the same time, there are so many advents which are happening at image level, and image as well as video level, I would say, where people are captured through different types of image, which is capturing through all the radiations, and giving us different aspects of knowledge which was not there earlier, and hence things are much more easier uh, uh, to diagnose now, I would say, before, because if you know what disease is or what are the early symptoms to a disease, identifying anything becomes much more easier. We'll be seeing a couple of such examples as well. So AI-assisted medical analysis, drug discovery, medical risk prediction, AI-assisted robotic surgeries. Robotic surgeries is started in India, and there are so many hospitals in India. I come from Chennai, and which is actually called the health capital of India, and I have got that opportunity to see that how much AI is actually working with robotics, and there are so many companies which are coming up here, which are working with these type of devices, or at least using AI at different levels in medicine. AI is also used in space. AI is used in robotics. I just want you to refer this Boston Dynamics website and go there and see how those they are making or trying to mimic different animals' motion and gestures to make different type of robots. AI is always there in education. AI is coming up in NLP. You are seeing so many home-assisted devices, entertainment devices like Google Assistant and all these, which are helping you in which in a way are making your job much more easier. Yeah, artificial intelligence is also used in visual surveillance. Well, that just to have a comparison of what exactly why AI is coming up, and what are the good thing which is coming up with AI, and where exactly AI lacks. That will also clarify that where exactly human excel over artificial intelligence. So we can give all the you remember all the demanding tasks, dull tasks to artificial intelligence, because they can keep on calculating. They are available 24/7. They will help in repetitive work. They have they work on algorithms, so they have faster decision. They don't think too much, because as whatever that algorithm will say, and given a same set of situation, they will act in a similar way, because they will always be talking in terms of input and output. Redundancy and human error of calculation is also again reduced. So if you see the calculation which is a power with artificial intelligence, if you say where artificial intelligence lacks, then it is first of all the establishment cost, because when you want to shift that entire system, which is done by human at a time, shifting anything on artificial intelligence is going to take a lot of cost. Then it does not have work ethics, values, and emotions, and all these. Why I'm saying this, because you can give money to someone and bribe someone to do some wrong work if someone is a human, but you can do it to one of the bank employee, let us say, but you cannot bribe the entire bank to do the same thing for you, because there are so many people and all might not be convinced at the same time. So maybe all these malpractices are good, or is possible at certain level, but not at the highest level, or not with entirety. But if artificial intelligence systems are hacked somehow, then all of them will be there on the other side, and then which is definitely not a good situation. So this is these are some of the high risk, which is it is a high risk high gain kind of game with artificial intelligence, and it has got a potential of misuse, and it is still in the developing stage. Why we call it in a developing stage? Because there are three levels rather than three types, three levels of artificial intelligence, and I believe that we are still in the artificial narrow intelligence level, where our machine learning algorithm, these Alexa, Cortana, and Siri are still working somewhat for us, and they are very much limited to one type of job, not like human that they can drive car, and at the same time they can come to office, they can work for them, and then they can go home and they can do all the stuff over there as well. So they are very much limited. If Alexa is made to give you answers, they can find it and give those answers to you. They can find out some music. When you call it, they try to have some acoustic identification and give you some music out of that, but not all of them. The next level is artificial general intelligence, which is where we are going to shift in the next decade or so, where we'll be having such devices which can work as many as tasks integrated into one of the device. And if you just check your smartphones, like a few days back, a phone was only meant for calling and receiving calls. At the same time now, if you see music, if you see camera, they are such an integrated part of your mobile devices that no one ever thought that we are going to pay much more than the subsidiary things other than calling and receiving calls on a mobile phone, a device which is specifically made for calling and receiving calls. That has become so secondary, and I would say tertiary now, that we are. This also gives one example that how we are moving towards a generic system, a system which is good for everything. And the next level, of course, what we say is going to be artificial super intelligence, where machines will reach to a consciousness, and they will start thinking and developing emotions the way we do, but which is still a far-fetched dream, I would say. Then talking about artificial intelligence, there are so many terms which are combined together to use the term artificial intelligence. We have on one side, we have this natural language processing, which is a big area of artificial intelligence, neural networks, computer vision, and then we have machine learning and deep learning. So we have to have these understanding. These terms are so much overlap that we have to have their understanding as well. And again, you see in machine learning, there are a lot of deviations. I particularly work on the vision part of image processing and artificial intelligence. So this is how I see computer vision, and it is about the image processing. When you try to bring some intelligence into image processing, it becomes computer vision. So like any image processing related task, you see, you have an image, maybe it has got some motion blur, it has got some out of focus blur, you want to deblur it. This process is called image processing. If it has got some sort of salt and pepper noise into it, you want to denoise it. This is called image processing. If you want to do some sort of rectification in the image, maybe it's a histogram equalization or something, then it is called image processing. And right in between, you will see that you try to segment an image. There is an image, you want to segment the foreground out of the background, right? So the moment you perform these segmentation, which is still a task of image processing, you are working in a spatial domain, but you are also getting some information. Maybe when you segmented multiple objects, you are trying to identify that out of multiple segments, how many such segments are looking similar to that of a human. Let us say you identified 5 such segments which you have identified in an image, and you are calling them as human, and rest all the segments as non-human. So you are trying to infer some information out of the image. And this is exactly the moment when you cross the boundary of image processing and you jump towards computer vision. In computer vision, your input is an image, but the output, as they say, is some information, some inferences out of that image. In image processing, your input is an image. Your output is also an image, maybe an enhanced version of it. You wanted to deblur, denoise, or whatever you wanted to do. So that input and output both being an image that is just a general understanding, but you will find some deviations as well. But I hope you got what do I mean by computer vision. So this exactly is what do we mean by computer vision. We take images, we take a sequence of images, and then we try to infer it, and that gives some meaning to us, and it becomes image processing at that moment. Computer vision in that moment. So this precisely covers my first discussion, and now I'll try to speak a bit about biometrics. Biometrics, why I want to talk about biometrics, because it is a very interesting field, and it is an implementation of computer vision, and it assists largely in healthcare. So that is the perspective how we are going to see during my discussion. So what exactly is biometrics? It is basically a way of authentication. We have a generation of authentications, as you can see over here. We used to have a token-based system, like when you have a bank ATM card, or you have an ID card. So what exactly you do? You say that you have that thing, you have that card, you have that thing. Then comes another level, which is called knowledge-based system, when you say that you know that thing, like your username and password or your ATM PIN. And sometimes when you go for a token-based plus knowledge-based system, you say that you own an ID card which should be with you, and then you have that password which is known to you. Now we are shifting to the third level, where you are that thing, and this is what you call as biometric. Biometric means you know what exactly it is. So I'll just share a few pictures, and I hope you know all of them based on some of the property which you can recognize very well. So if you see, there are a few caricatures and animates. If you see, with that also you can identify who these people are. So this is where our potential is. We are very strong. But would you like to calculate the maths which is there next to it? Obviously we can, but we don't prefer to. And this is where we lack from the machine. So the understanding is very clear. Computers are faster, humans are intelligent, and when we want to bring this intelligent artificially to these computers, because we know that they are faster, we are intelligent. You cannot make us much more faster, but they are faster. We'll try to make them intelligent, and when we try to do that, we call it artificial intelligence. So if you see, we try to mimic the intelligence. We try to mimic the intelligence of our natural intelligence, and we try to feed it into these devices. So what exactly happens? How do you identify any person when you see their images? Do you identify bit by bit of everything that you see into that person? Not necessarily. You identify few features, few global features, the way the nose is looking around, the way the eyes are there, and all these things you remember. And when you see this person say one more time, you try to match the same thing. Similar thing happens here. There is no pixel by pixel matching when two images of same person or different person appears. They take the images and try to identify few features out of it. And based on that feature, when these features are matching once again in the another image sample, then they are called to be same, or they are called to be different person. So this is how intelligence is mimicked artificially. So biometric, we already know, is is a Greek word, and it contains bio and metriki. It means to measure something which is present in our body. So we have physiological and behavioral parts of biometric, and physiological biometric is something that we possess in our body, like the fingerprint, palm print, iris, and all this. Behavioral one is something that exists in our behavior, like the way we walk, the way we press our keystrokes, mouse movement, our signature pattern. All these are part of our behavior. Behavioral ones are not as strong as physiological ones, but of course, you don't need to touch, or you don't need any physical contact to measure someone's behavioral biometric. To see if you want to give a fingerprint, you need to be physically coming and giving it over somewhere. So sometimes you see people are turning germophobic. Even before pandemic, there was a huge movement in European countries where people don't want to touch something that someone has already touched, and hence people are slightly moving away with these physiological biometric, and there this behavioral biometric can be very handy. Although the chances are there that behavioral biometric can be spoofed much more easier. So this is just a list of biometric versus behavioral trait. The same thing can also be done at commercial versus experimental level, and based on feature types as well. So this demo is just to see that on one of my experiment where I have tried to propose lip pattern as a unique pattern, and I worked on 3 different types of feature. One on the local features. Local features means the lip patterns, like our finger patterns, they also have this pattern, and you can find out these local features over there. Lep also have this global feature, that contour features, the way our entire lip shape look like. So local plus global feature works on a spatial domain. But when we start speaking something, then it is working in a time domain. We call it as temporal domain. So like if you make someone to speak something like, let's say, good morning, to 10 different people, there will be different way in which their lips will be moving to speak the same word. So this again makes a temporal feature. And a combination of all these 3 will make lip as a very strong feature because we are using local, global, as well as temporal feature, and may act very strongly. So a few articles are there for your reference that I'm using to prove this as a biometric feature. Authentication using a biometric feature may have these steps. I'll just skip these points. You acquire an image, pre-process it, features, you extract, perform some machine learning algorithms, and find accuracy and invariance. So just one point, invariance is very important in declaring something as a biometric trait, because it has to have an invariant. Like lip has this limitation that during summer the lines might be very prompt, but during winters, when there are lip chapping, then these prints might not be very much clear. Similarly, fingerprints also, which are although very reliable, but you see those who are working very hard, they don't have these fingerprints over here if they are using their hand for it. Or musicians, percussionists, those who are playing tabla and all these type of music, they find these features are gone. So so this is one of the limitations. Some features are also getting varied with age. So age invariance is also very much essential. And then there are other challenges like databases and soft biometric. Soft biometric is something based on which we cannot accept someone, but maybe we can reject, like height as a biometric, let us say. So based on someone's height, you cannot accept that, okay, this person is X or this person is Y, but you can definitely reject someone that this is definitely not X or this is definitely not Y. So these are there. Some of the features are fingerprint that you already know, and I'll skip this. And this is from the same research article that got published, I think, a decade ago, where you can see on this side we have a few features in the number 14, 16, and 17 features, SIFT features, local features on different persons' lip. And on the other side, we have features which are at least more than 100 for those cases where the lips are of the same person. And also it has a scaling variance. You can see one lip being smaller, the other one being bigger. So this local algorithm was working very fine. We also worked with contour features. This, you can see that this is a global feature. And of course, we can make use of temporal feature that I have not included, like a video over here. So that can also be done. The another very important biometric is gait biometric, which is an example of behavioral biometric. Gait means the way we walk, the way we walk. So our way of walking is very, very particular, and this is based on this person can be identified. This has got a lot of medical implications as well, not only for gait as a biometrics, means for identification, where it may or may not perform that well, but for healthcare, this gait is used very hugely, especially for patients who were a sports player and they are recovering. So their walking pattern is monitored every day, and how the pattern is changing and coming to a normal walking pattern, this is observed. And the swing phase and the stance phase and the movement during stance phase, the plantar flex and dorsiflexion, and all these steps are identified very clearly to identify the recovery of a person with the help of these video analytics. Anyway, so we'll be coming on to that. And another type of biometric, or another aspect of biometric that I want to highlight, is the biometric that we use for animal. Of course, this is one of the big area based on their biometric properties and the images that we use to capture in biometric. There is a good chance that we can also identify about their health, their present situation, their even their mood swings. Everything can be identified with their physical properties, which can be captured using any camera, apart from their biometric properties. So you see, it's been animal, especially in this Indian subcontinent, is a huge property for any human being, especially in villages, if you see. And there are much needed identification which is required for these animals as well. And if you see, there are tag based, and there are stamping based, and there are other ways through which we try to give a unique symbol or unique mark to our animal, which at times could be unethical, could be you can say it could be troublesome because it is causing them some pain, and at the same time they are vulnerable. They might not be the best way, can be stolen even after that, and that is why biometric comes into the picture. So this is one of the database that we have created, which contains a lot of animal, and it is a bit unconstrained. So you can see like tongue and the nose kind of situation, where few of the muzzle properties. This the second row indicates the muzzle, which is again a unique set of feature, like as that of our fingerprint or lip, and it is also giving us good pattern when we are using any local feature extractor to identify these animals. So we have all the varieties of images that we have created over here, especially with the South Indian cattle species that are available to us. You can see they look clearly very different than that of the one that you see in the North Indian varieties, especially if you see their horn patterns, you can identify. So this also says that the breed identification is very much possible, and age group classification is also possible. At the same time, their gender classification is also possible. So there is a huge scope that lies with the animal as well. And once all these information can be extracted, then their health is quite related, or these information will assist in getting their health in a big way. Because if you see the previous case, I just want to show you where we have wet muscles. So the amount of wetness on any muscle gives information about their health care. Similarly, if you see the overall body and the profile body, as you can see here in low light and in few of the shadow cases, they also give a lot of information about their healthcare, and they are widely used, and they are widely used in places. These are a couple of example where we tried local feature with muscles, and auto-prone muscles are giving a really good set of features. And these are a few features where we have established a separate feature. This was using SIFT feature, this was using case feature, and this is the dog muscle that we have implemented, and still getting good accuracies. So this is about biometric, and we have a lot of future with biometrics as well. So having discussed about biometrics and a bit about artificial intelligence, now I'll take up two case studies. These case studies will give us some of the hint how artificial intelligence are used in the domain of healthcare, and sometimes you see they are directly used in the cases of healthcare, like when we try to identify softer tissues and harder tissues, and to predict different type of diseases, and different presence of different types of lumps and all these things. During the time of COVID, there are symptoms of pneumonia which on that particular time domain are used with to identify corona cases based on the X-ray images itself. So there are many assistants which are already there with image processing, but they help in healthcare very much directly. There are other scopes of artificial intelligence which bridges the environment, or it creates an environment where healthcare can be done in a better way. And my examples are also included like that. So the first case is about optimal placement of camera for gait pattern recognition. So we have already discussed, and the second one is going to be spatio temporal optical blob reconstruction on a temporal feature set for placoidal cell migration. I'll be coming on to that, but let's talk about optimal placement of camera for gait pattern recognition. So now we already know that gait, what is gait, and the way we walk is called gait. We have, for both the legs, we have this stance phase at which the foot is lying or resting onto the ground, and there will be a swing phase, and stance phase is of course bigger, and the swing phase is going to be smaller. So 60-40 is the usual ratio. And from first heel strike to the heel strike, once again we call this as the complete gait cycle. Now the challenge is that given an open area, let us say that a hostel corridor, or maybe there is a big place where we want to identify someone based on their gait, or we just want to capture someone's gait feature for their best health measurement. So what are the camera placements which are possible? So there are many cameras where we can make them, place them, or there could be some pre-identified ramp where we can ask people to walk. So if the people are walking in that direction, then we can capture it from certain angle, and we can say something about their gait information. Now, already we have talked about gait, so I'll come to this slide later. Yeah, so this information is that you see if the way person is walking, and the camera is placed exactly in front of it. So what will happen? Camera, you know, is a monoocular device. And as the person will go away from the view of the camera, as you can see, if my hand is placed away from the camera, it will appear to be deteriorating in width as well as length. This is called perspective distortion. So the perspective distortion with respect to camera plays a huge role when we are capturing any particular device, so any particular movement. So what movement is visible from a close camera might be gone when the subject is far away. So knowing this, that what exactly could be the angle from where a camera can capture a particular situation is very important. And we are going to see the usage of artificial intelligence in the same field over here. So this is just a small experiment that we have done, and we have made a subject to move towards the camera, making an angle of 45 degree with respect to camera and making an angle of 90 degree with respect to the view of camera. And as you can see, these are the three graphs which indicates the pattern in which the width or height is changing. So if we are identifying a human, we are actually putting a bounding box onto it. So bounding box is having two properties now, width as well as height. So if we plot width, the pattern in which width is changing or height is changing, we will see that there is an increase over here in the diagram A, in the subfigure A, which indicates the subject is coming closer to the camera, right? So what feature you can see when it is coming closer over here in this region is not visible over here, which clearly indicates that camera having an angle of 0 degree with respect to the view angle is definitely not the best way to capture gate features. If we just make this as pi by 4, you can see that some of the gate features are visible, but the pattern, because the width, the stride strength is not going to change. But look at the measurement over here. It is coming this much. It is coming slightly more, and it is coming slightly more over here. So again, they are not very best captured when the angle is theta is equal to pi by 4. But if it is exactly a pi by 2, that is view angle is like this and the walking is happening 90 degree. So we can see that the gate features are best captured. Gate features are best captured. If we do some better pre-processing and all those algorithms, then we can get this graph even more better. But the features, gate features are much more clear, and there is no effect of perspective distortion. This angle decrease is reduced, so the range is parallel, and hence we can say that having an angle of pi by 2 with respect to the motion angle is the best angle for camera placement. So having established this fact that this is going to be the best angle, we will see that what are the ways we can do. So these are some of the steps that are enlisted. I'll let you know what we have done over here. So we have first of all discretized the way a person can move in an open corridor. So we are not considering that situation that we can make a people to walk in a ramp, because in that case, again, this much information is sufficient. The person is walking in this ramp, let us place the camera 90 degree to it. But we are discussing about a situation where there is an open corridor and people can walk in any of the direction. And when we don't know where the person is walking, so where to place the camera, where people might come or where they might not come, that information we don't have. So there, what should be the optimal placement of camera so that we can identify everyone based on their gait? This is the challenge. So we are thinking that let us discretize the way people move and we see on a camera. So we have identified these different discrete directions, 8 different directions, and we went ahead with these information. Any such information, any movement, we will try to discretize into any of them. Now, what you can see over here is a big corridor, in a square corridor, and we have taken an orthogonal camera, just top of it, and overhead camera, and we have tried to identify loci of multiple people walking from one place to another. So these are the two maybe two entry gates, or this was the main entry gate, and people can go to two different places from here, and this is what the locus of many people walking around is turns out to be. So based on that, we will identify each and every such boxes, that what we are going to find it. Let us say that there are multiple pixels which are available to it, and we find that there are these type of region where we don't find any locus, like these cases. No one was moving during that time. So these are not leading towards any information. There are some cases where people are moving all around in all the other direction, and still we cannot say anything like this. See, one people is moving like this, another is moving like this. So these boxes are not giving any information to us, conclusive information, I should say. If you see, there are few boxes where you see that people have got one pattern in which they are moving. So like you see over here, most of the people are straight. If you see this particular box, most of the people are moving in this direction. So these are the ones which are giving us some clue that if we observe subject at this point, then most of the people can be identified at this angle. So our camera must be placed in such an angle that it is orthogonal to this particular view. So we are actually what we are doing is that whatever is the leading direction, we are making these are different arrows. These are the prevailing arrow of that particular direction, which we will go for a thresholding, and the most prominent direction will be the direction. So this way we will make multiple diagrams, multiple arrows for all the informative ones, the grid including unique direction of movement, and then we will try to find out its average by finding the loci. And then when we have a generic loci, then we will try to find orthogonal lines from all of this, from all these lines, and we will see what are the regions where these orthogonal lines are intersecting each other. So these are some of the region. The darkness indicate the more prominence, the more number of lines which are intersecting over there. So these are some of the places where if we place the camera, we can capture people in the orthogonal way. And once we capture them in an orthogonal way, it will help us in capturing their gate information in a very nice way. And this is the idea how we are implementing artificial intelligence to make an environment for gate capturing. So this is actually the experiment that we have done on that open corridor, and we were not having the over-the-top camera, so you can see that the picture is taken through a particular angle, but then we applied our algorithms, and then we have tried to take the optical flow for individual persons movement. As you can see, we have taken their optical flow, we have traced down their path, and we have tried to identify these loci. So this is the actual experiment that we have performed. This is one of the sample grid that we have actually captured, and this is the kind of histogram of different directions. You can see this is the leading direction, and all the neighboring directions are also visible. So we can say that this could be the leading direction. So we have made arrow accordingly, according to this direction. So this is how we have done, and this is the optical flow of all the direction that we have got. Since, as I said, that we have a camera at particular angle, so we applied our homography algorithms to get the actual positions, actual loci in the top view. And then these are the 3D images where like we have shown you the darkness. So the height is showing the same thing over here for best camera placement. So this concludes my first point, that how we have used this one. The second, of course, usage is the spatial and the temporal features for optical blob reconstruction of placoidal cell migration. And to tell you something, that this was at exactly the time when I was working with a surveillance task, and I was told to find out the pedestrian when they are walking in an open area and they don't get occluded. They often get occluded by some solid object, so they get hidden. The view is getting hidden, is called occlusion. So they were getting occluded, and what to do in this kind of situation. So the same thing, the same problem was also there with placoidal cell migration when we are trying to identify. So what happens is that because of some static occluder, and they are moving, and when they go behind it, then they are identified as two different objects, and the tracking fails during that time. So based on the speed at which they were moving in the temporal domain, we may identify that the same subject has bifurcated at a particular point because of some occluder. And then they, when that occluder space is ending up, then they re-identify themselves and they recombine themselves. So this is what we have tried to do with the optical flow of individual point, individual pixel, as we see on a temporal domain. So we nullified such blobs which are having all the chaos, all the directions. If you see, they are moving in the same direction, and this pixels does not have information. We believe that they are part of actually the same object, but because of some occluder, they are not visible. So we are trying to unify such blobs. So these cases is blob nullification. We identified blob unification and also blob bifurcation. So like these set of blobs having this direction, these set of blobs are having this direction. So we bifurcate it as two different objects. So this is how we have used it, and this you can see the actual image of a placoidal cell, where when it is migrating, these three are shown here in the highlight. When they are migrating, then there is actually an image sequence, if you see clearly over here. So the one in the bottom, if you see towards the frame number 8, then it has one linear motion towards x-axis, and that has been identified as the same object. If you see this red one, so it has got it finished here, and it has never appeared here for a few frames. But when it reappeared, you can see a yellow line over here. So it has been identified as a different object. On the other hand, the problem issue, which is about this big one, which is getting occluded for few frames over here, as you can see. It is almost occluded here and being identified as two objects. But our algorithm is is connecting it with the green line itself, indicating that they are actually part of the same object. Now, the advantage that we are getting out of it is that whenever we are trying to study a particular cell, or whenever we are trying to identify the movement of one particular cell, so we can say it with these computer vision based algorithms that the same object is continuing. And in future, when this occluder is finished, that occluded region is finished, then we can also go with the unification algorithm, and we can identify them as one single object itself. So these are a couple of test cases that I would say, and a few books and references on biometrics if you are using it. And that's it. Thank you. And to finish this, I will just give you this information. This is Sharbat Gula. I hope you might be knowing this case, where she has been identified based on her iris biometric feature, which is taken by some photographer 18 years later, based on her image. So that's it from my side. Thank you. Thank you very much.
Participants, if you are having any kind of queries, you may ask from sir related to this topic. Please welcome. If you are having any kind of query, any kind of question, ask from sir. Anyone? No? Okay. So thank you so much, Dr. Rahul Aman sir, for your valuable time. Your respect of has provided us with invaluable insights about artificial intelligence, its purpose, applications, risk involved in it. You also talk about its types, image processing, and computer vision. Then you informed us about gait and biometrics in humans and animals, and how computer vision helps in healthcare, and how humans are identified using it. You also discussed about spatio-temporal optical block reconstruction. uh, Thank you again. I am sure our participants have attained a better understanding about all these topics. Thank you again, sir, for taking about your valuable time to impart us with your knowledge. Thank you so much, Rahul Aman, sir.
Thank you. Thank you. Thank you.
Okay. Our next resource person has come online, Dr. Jiten Kumar from BIT Bangalore. So, welcome, sir.
Thank you. Thank you so much, sir. Am I
Thank you,
audible?
sir. Thank you, sir, for accepting our invitation. On behalf of our institute, I cordially welcome you. Sir, we are honored to have with you us. So I will introduce about sir. Dr. Jiten Kumar is having over 20 years of experiences in academics like teaching, research, training, project, consulting, and academics administrations like HOD, program director, program coordinator, program leader, etc. He had served over 5 years in various firms like Professor Technology Gurgaon, DataNet India Private Limited Delhi, Cassette Pharmaceutical Limited Bhiwadi, CSC Private Limited Delhi, and many more at various designations like consultant, technical analyst, data scientist, statistician, research editor, etc. Presently, Dr. Kumar has been the Associate Professor of Statistics and Statistical Science, Data Science and Analytics at School of Advanced Sciences, Bangalore Institute of Technology, Bangalore, Tamil Nadu, India. He is the coordinator of the program MSc Data Science. Prior to the current assignment, Dr. Kumar had served MIT University, Noida for almost 13 years at MIT Institute of Applied Sciences and MIT Business School. Dr. Kumar had served MIT University Dubai campus. Dr. Kumar has authored and co-authored few books besides having various national and international research papers, etc. His research focuses on application of statistics, modeling and simulation in the field of like criminology, crime hotspot, crime clustering, epidemiology, biostatistics, statistical modeling for forensic research and analysis, statistical inference, econometrics, multivariate data analysis, etc. As a head Department of Statistics, MIT University, Noida, for around 5 years, he had acquired and developed substantial skill on academic development and administration. He has been the member of various academic and research committee at AUUP Noida, like member faculty interview panel, SRC, DRC, and FRC, BOS, PRC, CRC, AAAB, Academic Council. He has guided over 200 student dissertation and helped more than 20 PhD research scholars towards their thesis work. Dr. Kumar presently the lifetime member of various national and international organizations, associations, and scientific bodies, societies of repute like the Indian Science Congress Association, Kolkata, Institute of Actuaries, Mumbai, India, National Book Trust of India, New Delhi, Indian Mathematical Association, etc. Sir, it's an honorable moment for our institute to have your prestigious presence in today's event. We are truly inspired by your deeds. I hereby request Dr. Jiten Kumar, sir, to alignment our minds with his expert talk. Sir, please.
Thank you so much. Thank you so much, sir, for such a very proficient and very impressive introductions. I would be obliged to the organizations, Triple IT Bhagalpur, the top management, respected director, Dr. Chaubeso, and entire Triple IT family with all fraternities. We are planning and we are delivering for the benefit of the society this certificate course. So I hope so. This session, though it is the last session probably of the day, and most of the audience probably have synergized or maybe otherwise, but I try to make it as simple as possible, and I do not going to burden them on a specific research kind of stuff. Rather, at the moment, my objective is to explore and harness a very useful tool of data analytics and very widely prevalent tools, that is simulation and modeling. So I'll try to make it, because majority of the people and researcher, even the industry people, they are working on simulation. So my objective today is to make it done in a way that the participants would able to understand and conceptualize all related concepts related to foundations of simulation modeling. Let me share the slide for a moment. I'll try to share it. Just a minute. Just a minute. How should it comes to? How do can be a Google Meet full? Chavi sir, can you help me how to share? I am trying to.
Sir, arrow. Just right to third button, arrow, present now.
Present now, okay.
Yes, sir. Present now and then entire screen.
Okay, entire screen. Okay. Just
Yeah.
okay.
In which PPT, what you want to see, so you may show it. Sir.
Okay, sir. It's coming, I think.
Thank you, sir.
1 minute. Is it visible, sir?
Sir, right now, no. Yes, sir. The screen has been shared and visible, sir.
Okay.
Yes, just F5, sir, for full screen.
Yes.
PPT. Yeah.
Okay, sir. So, thank you so much for helping me. Now I'll try to scroll it one by one, and just give me that whether scrolling is done or not. Is it happening, sir?
Yes, sir. Moving,
Fine.
sir.
Fine. Thank you so much for all kind of discussions. Thank you so much for your cooperation. So here we are running the 5 days STC on artificial intelligence and data science in healthcare sector. In particular sector, the simulation is very much useful. So I have been assigned a topic, decision modeling and simulation. My objective here to make the concept very simple, very much understandable, and that's why I have set 3 objectives here. To develop understanding of decision modeling, first we'll understand what is model, what is a decision modeling, and something fundamentals about decision modeling. Second is to describe the methods to generate the random number. Though I cannot go to much depth into that, but yes, some of the basic statistical methods I would like to highlight, that the students and the participants must be going to depth after the session so that they can get benefit of it in a day-to-day applications. And third, I'll try to just illustrate few examples. So simulation in practice, how we can initiate it, some applications. So let me have a basic question, what a model is. Usually people confuse with formula, definitions, equations, and a model. So a model is a replica of real-time entities to develop a precise and viable solution. This is basically more theoretical. So let's have go to the example side. Suppose I cite one example, force is equal to mass into acceleration. Can we say it model or not? Some necessary condition has to be satisfied. In this, we can observe that this is the Newton's law, and this formula particularly derived from second law. So here force is external force applied on a body, mass is the mass of an object under consideration, and a small a denote the acceleration generated due to force. But the question is how we can make sure that it is a model. Do we have certain specific condition to satisfy for a model, or can we say every formula is a model? Definitely not. Every formula cannot be a model. So there must be a clear cut understanding about the model. Similarly, if I give you another example like uh, Poisson law in statistical theories and a law of distribution, if x is a random variable follows Poisson distribution, then probability of x is equal to x must be given by e raised to power minus mu raised to power x upon x factorial, where this random variable x will take the value 0, 1, 2 and so on. So again the question is it a Poisson model, is a model, or it is just a equation? So in addressing such kind of question, how do we make sure that a given formula is a model truly or not? There are certain basic conditions. First is, in every model, there must exist a functional relationship. So here you can see the capital F is functionally related to acceleration applied in the body. So whatever the acceleration produced, that will depend upon external force applied, or if you produce the acceleration, it would reflect it into force. So force and A is a functionally related, and mass, capital mass of an object is a parameter here. So A is variable, M is a parameter, F is output variable or extraneous variable, and F is functionally related to A. The last condition is Newton theorem, because this formula is applicable only to a inertial mass. This formula will not work where mass is non-inertial. That means if you are going to a non-inertial frame, this formula do not work. In theory of relativity or where there is a concept of mass defect, you cannot expect this formula to be work. Similarly, if you see this Poisson theorem, Poisson model, here you can see mu is the parameter of the model. This y means output variable, that is the probability x is equal to x is a variable that if you put for every value of random variable x is equal to 0, 1, 2, 3 in this model, if parameter mu is known to you, this probability can be computed very easily. So here functional relation exists, parameter mu is existing, and the random variable x is there. More important, Poisson law cannot be applicable to every cases. That's why it is applicable under certain empirical conditions. What are those? It would be true only when the number of trials, all those cases where the number of trials is very large and probability of success is very small. Let's take example. Suppose you are considering the flight from Delhi, Chennai and other places, thousands of flights every day as a routine task, taking off and landing on. But the probability of getting crash is rarest of the rare. It may be happen in 5-year, 10-year or 20-year, one single cases. Similarly, the cases of crimes, right? A person do not have every day the chance of getting bullet, or maybe some criminals meet and some sort happens in the brain, and even some sort happen in the brain, the person may survive. So those are very rarest of the rare phenomenon. So wherever in the life, in a real-time problem, you will find such kind of thing like in a criminology, in a epidemiology, in a spatio-temporal analysis, and many process. you can apply Poisson model. So these empirical laws, number one. Number two, the independent input variable, random variable X. Number three, the parameter mu. And number four, the output variable probability X is equal to X. All these existing together. Summary of my discussion through these two examples, I would like to clear that every formula and every equation cannot be a model. So very start point for all audience is that you should be very clear about whether you are handling a model or you are just handling a mathematical formula. Unless until you not be clear, then your entire process of computing probably suffer through some inherent errors, and probably it take to you towards the wrong side of decision making. Now I am moving to next slide. Here I would like to summarize this in a formal way. What I say here, so we observe that for a model the necessary conditions are the availability of the measurable, that means variables, a specific parameters, certain laws, maybe in a form of axiom, maybe in a form of lemma, assumptions, postulates, or any other initial conditions or restrictions, maybe boundary conditions set forth, etc. And there must be exist a functional relationship among the variables between exogenous and endogenous, or you can say between dependent and independent. So variables and parameters all are functionally being defined in a formal way. Next level of discussion is, so I hope the clarity about the model is almost, there is no doubt now that what is model and what is not a model. At the end of the session, I may ask some of the basic questions from the audience, or audience may ask to me, and we can discuss it at the end. Suppose I say simple interest is equal to PRT by 100, is it a model or not? So the answer you can just think on it. When I finish the session, some of you will give me the answer. Now I move to next level. Next level is decision modeling, because today's in the entire world, whether it is a scientific community or the econometric people or in a business class decision making, all about the success, all about around moving around the decision, correct decisions. So there is a need of decision modeling. How we can understand a decision modeling, how it is different than other modeling, mathematical modeling or stochastic modeling, or there is some similarity in between that. So here I say that decision modeling is a scientific approach to arrive at a decision, or you can say that enable you in decision making process, especially suitable to a situation when the outcomes are not certain. That means where the output is not certain, outputs are the random in nature. As such, risk involved in decision is higher. For example, if you toss a coin, you don't know whether it will head will come or the tail will come. Similarly, when you do a project in any field, as a suppose new venture, you are having expectation of success, but you are not having too much expectation about failure. So the question is, through decision modeling, if we streamline our process, we can make our failure as minimal as possible. Nobody can make sure, no tools in the world so far, no artificial intelligence and machine learning, no deep learning, and even in future, robust technology is not going to solve the entire problem and make you error free, and you are saying that yes, now there is no chances of any risk. It never be happen, whether the irrespective of the scientific development and its level. So we can do the best using decision modeling, minimize our risk. So we may refer to our decision modeling as a quantitative analysis more and more, since it is being used in the management sciences by the top management people, whether it is a field of education or it is a field of business, commerce, scientific organization. The top people take decisions. So decision modeling is highly useful for managerial sciences. Let's move to develop the understanding of types of decision modeling. Basically, I make it very simple and given it deterministic and probabilistic decision modeling. So far as deterministic modeling is concerned, that became a classical concept that is well known to people, and nowadays very few people are working on deterministic model. Majority of the projects, majority of the works in industries, and any news, new kind of ideas can easily be work on with probabilistic nature. So a deterministic model means a model with complete certainty. I have written it here, a model with complete certainty. So there is no risk involved much, and therefore no adventure. There is no much excitement. There is no much thrill in a process of decision making. So, which is the least important in contemporary context. Such a model assumes that all the relevant input in form of data values are known with certainty. This is really not very true. If we assume it, it is really a very dashy assumptions. But generally, deterministic school of thought always assume that whatever the relevant input you require, it is being certainly available to you. For example, in optimization theories, linear programming, the assignment problem, transportation problem, goal programming, integer programming, and many more, inventory management and all. There are a lot of cases where you purely deterministic in nature, right? But their limitations are too much. They are very hardcore. They are not flexible, and they cannot be ready. Those models cannot ready to accommodate the new challenges and the new task. And therefore, we are deviating and shifting from deterministic model to probabilistic and stochastic model. The next level is, here I would like to give a brief about probabilistic model. In contrast to deterministic model, probabilistic models assume that some input data values are not known. I make it capital letter to highlight it with certainty. What does it means? It means that values of some important variables and parameters will not be known, and we have to estimate it before coming at final decision. So estimation is an important process here. I could have to underline it, but I leave it to you. I say first very important steps in a probabilistic modeling, that challenge to do the proper estimation, because estimation itself is not easy. There is a lot of chances that most of the accuracy level challenges comes at the stage of estimation. Later on, the challenges persist at the level of testing too, because estimation further requires to be tested whether it's working well or it's really are well within a stipulated probabilistic limit. We call it confidence limit, whether it is related to estimation or it is related to prediction. So estimation is a challenge in a stochastic modeling, but if you do it very nicely, definitely the stochastic modeling is going to resolve a lot of cases with the support of additional information, maybe in a Bayesian model incorporation, maybe incorporation of other amalgamation of computer sciences ideas, programming ideas, computational speed ideas, etc. It make the probabilistic modeling more and more successful. So now the question is, how does it work? So we should know how it work it and what are the simple process, very elementary, very simple way to work it. So probabilistic modeling uses probabilities values to incorporate the uncertainty. This is the basic principle. This is the working. The entire probabilistic modeling is working on probabilistic idea, and that's why I have written it here. Probabilistic models use probabilities values to incorporate the uncertainties. Next, there is a important point that I would like to highlight it here in a form of remark, because uncertainties plays vital role in probabilistic modeling. Some knowledge of basic probabilities distribution of any kind, maybe discrete distributions. You heard of many standard discrete distribution like binomial, Poisson, geometric, etc. and also continuous distribution, T distribution, normal distribution, Babel distribution, Gompertz distribution, Pareto distribution, and there are many more distributions of great use, logistic distribution, etc. And then some of the distribution is neither purely discrete and nor purely continuous. Therefore, we categorize those distribution as mixed distribution. That means a distribution part of which following and part of which is using a discrete random variable as their building blocks, and part of those models are using continuous random variable as their building blocks. So in together, when you handle the real-time situation, nothing is pure and nothing is impure. Nothing is purely discrete, nothing is purely continuous. In fact, the majority of the events in the nature is of mixed kind. So that's why a great skill and practice is required to develop and handle a idea of mixed distribution. Here generally the researchers fail and they commit mistake because by habit they prefer to go the well set standard distribution, and their thinking always go, okay, yeah, this is what Poisson is there, this is what normal is there. They never think in between that part of Poisson and part of normal. So that is one point that I would like to highlight at this stage so that you can handle it very, very carefully. Now, I would like to address another question. What are the steps involved? Because if simulation and decision modeling, they are coming to a big role in a management science, we must know the process or the steps involved in a decision modeling process in a real world situation. So here I would highlight it three basic steps in a decision modeling. One is called formulation stage. This is most challenging stage because here is the challenge of model building. First challenge, like variable selection. If you choose incorrect variable in your model, or you can choose or you can think of developing a model that is not going to solve your problem, then a little or a small mistakes will be a problem in a later stage of your computation. Second step is called solution stage, and the third stage is called, that is the final stage, implication stage, or you can say interpretation stage. So we can elaborate these three steps: formulation, solution, and implication with little more in a more simple way. First, we'll concentrate on formulation stage. Here what we do, we are defining the problem. As you know that every research topic or every problem, if need to be solved, you must be very much clear about your problem, that what you are going to address to. So here also in a simulation modeling and decision modeling, defining the problem is a very basic and very first step. Second thing is developing a model. That means you are going to develop a relationship between dependent and independent variable, endogenous and exogenous variable, functional relationship you are going to inquire. You are going to compare one variable with another. You are going to process the information. You are going to clean the information. You are going to identify outliers before putting your values in the model. And you are going to also identify the leverage points or influential points in your model building exercises. So these steps, formulation stage, is really a very challenging stage, and probably this stage should be the error free. If you anyone commit mistake at this stage, the latter stage have no meaning. So defining the problem, developing a model, and then acquiring the input data. This is again a very challenging task because you can't control over the data. You take data whether in a structured form or in an unstructured form, your challenges is always be there. Even the structured data is there, the elements of biasness and sampling error is very high. Even the data is unstructured, then you can say your challenges will be further very high, because billions of data, unstructured data is coming within a few time, and you can see that Twitter and other things, social platform and all, the information dynamics is very, very complicated. And here is the game of all data science applications and all applications of machine learning. So these stages require tremendous careful carefulness to go for first formulation stage. Once you complete the formulation stage, you could move to next level of decision modeling. It is called solution stage. In a solution stage of decision modeling, you can do what? First, you think of developing a solution in terms of mathematical formulation. So, the strong mathematical input is always necessary for all sciences. And as you know, mathematics is the mother of all sciences. That's why you can say that at least moderate level of mathematical input must be in this particular domain of knowledge required. So developing a solution, especially the feasible solution, that solution could be practically relevant as well as mathematically and statistically relevant. A solution only practically relevant could not be accepted. A solution only statistically relevant cannot be accepted. So a accepted solution is a feasible solution only when they satisfy both empirical ideas as well as practical need. The second thing is testing the solution. Once you get the solution, you test it whether it's coming well as per your plan, whether it's coming well within your expected range, whether it's suitably justifying all the logics and concept which you incorporated at the beginning of your model building, and that's why testing is essential. Then the last stage is basically the implication stage. In an implication stage, purely it is analytical stage. So analyzing the results and doing the sensitivity analysis are very important tools. In a sensitivity analysis is a purely diagnostic in nature as well as purely measurable. To change one minor change in input should be reflected by what amount in the output. That kind of measurement is called sensitivity analysis. And in a modern model building exercise, sensitivity analysis has lot of focus, because if your model is not sensible, then definitely your model will no longer remain flexible, no longer remain capable to incorporate new changes too. And therefore, sensitivity analysis at this stage is very, very important. And the final stage is implementing the result and preparing a report, taking a decision. That means once you implement the result, you can take action, you are free to take action, and you can expect your action is going to bear a fruit. Now, next level is coming to fine decision modeling process and all those things happen. But now I'm moving to what is simulation and why it is so important. Do we really mean about it? So what are the some fundamental things that need to be refreshing and that need to be nurtured? So simulation basically is a term which is widely popular but least understood by many people. So to simulate means to duplicate the features of a real system. The idea is to imitate a real world situation with a mathematical formulation, mathematical model, to study its properties and operating characteristics, to draw conclusion and make action decisions based on results obtained from this simulation. So sometimes in later stages, after a few minutes, I make it a example, and you can see that how it is important. After that, we'll go for process of simulation, and again it is quite scientific and well defined, well structured, 7 steps process. The first stage is similar to like that: defining the problem, variable selection, construction of the model, specifies values of variable to be tested, conduct the simulation, that is called experimentation stage, then examine the results, and finally select the best possible action. So simulation again is a tool that finally making you or enabling you to come at best possible decision, especially when the outputs are very uncertain, especially when the risk involved seems to be very high. The next level is what are the advantages and disadvantages of simulation in day-to-day life? That need to be understood. Because once you understand the advantages and disadvantages, then you will be in a position whether you should go for a particular thing to simulate the idea or not. So very first advantages, few advantages I would like to discuss. I can't cover all, but at least the key advantages I must share with you and presenting here. First one is relatively straightforward and flexible. Simulation is a straightforward as well as flexible. Flexible enough to easily accommodate several changes to the problem scenario. And then the second advantage is it can be used to analyze large and complex real world situation that cannot be solved by using conventional decision model. For example, it may not be possible to build and solve a purely mathematical model of a city government system that incorporates important economic, social, environmental, and political factors, but simulation has been used successfully to model such urban system in Delhi, in Chennai, in Bangalore, in New York, and every big cities of the world. The hospital management, educational system, national and state economies, and even world food systems, and many more examples are there where simulation is a day-to-day norm, day-to-day practice. The third advantage is simulation allows what if kind of analysis. That means simulation allows what if type of questions, and a manager can handle several policy making decisions within a very short span of time, which is not being possible otherwise. The four very important advantage with simulation is it do not interfere with the real world system. This is very interesting. Simulation do not interfere with the real world system. With simulation experiment are done with the model, not on the system itself. I would like to give one example. Suppose you want to do measurement on the outer sphere of the sun. That means that is called protosphere. That what is the temperature actually you want to measure? Can we go there and do the measurement? Is it possible? Not at all. And there are many situations. For example, if you want to measure the number of bacterial densities and viruses and other microbes densities in the Mariana Trench, almost a trench a depth of ocean in Pacific Ocean that is almost more than Mount Everest height of depth. Can we go there actually to do any experiment? So in all such situation where physically you're not able to perform the experiment, you can do the simulation and you get it done. So any probabilistic event can be simulated 50,000 times, 1 lakh times, 10,000 times within a click with the use of computer and sophisticated programming and devices. And that's the beauty. That experimentation cannot be done physically even in a year, right? So this is the biggest advantage of simulation. And the next few advantages are, first one is, the fifth one is, the simulation allow us to study the interactive effect of individual components of variables to determine which ones are important. All inputs are not always equally important, and therefore it is very important that we can make use of simulation to selectively vary with each input or even in a combination of inputs together to identify the ones that most affect the results. And then the sixth advantage is time compression is possible with simulation. For example, the effects of ordering, advertisement, and many other policies over many months or the years can be obtained by a computer simulation model in a very short span of time. One more advantages with the simulation is it allows for the inclusion of real world complications that most decision model cannot allow to do it. So I hope these are the sufficient number of advantages to attract your mind and why to understand why simulation is so much popular nowadays from industry to corporate house to scientific bodies, especially in organization like DRDO, in organization like space technology, simulation and its practical implication nowadays is very prevalent and very much frequently done. Here, some of the disadvantages I would like to mention. This is because every system has some demerits. We must know what is wrong with simulation. The first thing is good simulation model can be very expensive and it's open for often take a long time. It is complicated process to develop a model. For example, if you want to develop a corporate planning model, it can take many years or many months. That's why simulation process seems to be easy, but actually it is not. So here again, the level of expertise matters a lot. That's why simulation team usually will be kept in any organization as a team of experienced people. Now the second disadvantages with simulation is simulation does not generate optimal solution. That means if I ask a question, do you feel that simulation is a optimization tool? Answer is absolutely no. Simulation never be an direct optimization tool. Rather, it enables us to go for or support to go for optimization process. But as such, it do not measure the optimization and do not is a tools cannot be categorized a tool of optimization. So we can see that simulation does not generate optimal solution to a problem as to other decision modeling techniques like LPP, transportation problem, goal programming, integer programming, fractional factorial, and other kind of deterministic modeling process. The next disadvantage with simulation is simulation may be trial and error method. That means there is no objectivity in simulation process. Different people, different mind have different way to do it because it is idea enabling exercise. So simulation may be a trial and error approach and that can produce different solution in repeated runs, probably for a time being create some confusion. Which solution is the best? Which solution will go for? A kind of little confusion probably will emerge due to simulations, and that's why it is treated as though it is a merit also, but largely or majority it's treated as a demerit. And the fourth, and probably I ignore the others, but fourth important disadvantage is simulation model does not produce answer by itself. As I said you, simulation is more a facilitator than a tool. So simulation model does not produce answers by itself. So managers must generate all the conditions and constraints within their organization for solutions that they want to examine. So these are the basic four kind of disadvantages of a simulation modeling. Now I'll come to one more negative point. Each simulation model is unique. Its solutions and inferences are not usually transferable to other problems. That means if you develop a model, you can't transfer the solution of this model to another simulation model because the solution is unique in nature and one solution will be suitable to those particular model also only. Therefore, it would be treated as a another unique disadvantages of simulation. I thought now with 7 points of advantages and 5 points of disadvantages, almost I have a notion that you having a clarity when you need to use simulations and how you cannot go for that, why we cannot go for that. So how and why related to decision of simulation modeling is one of the important things which everyone must do before going for simulation process. One of the most common simulation process methods, you can say, it is called MCS, Monte Carlo simulation. Though there are some advanced methods of simulation nowadays is coming that is based on purely transition probabilities, purely stochastic probability zone, but I am discarding for this discussion because that would not be possible to cover all those things in a 1 and 1 hour half hour session. So that's why I focused on the most fundamental things for today's discussion. Now I will take you few minutes discussion on Monte Carlo simulation and would like to demonstrate it with a small example how it works in a very simple way. Let me first give the meaning of MC simulation, Monte Carlo simulation, how it works. So you can see in a Monte Carlo simulation method, when a problem contains elements that exhibit chance or probability in their behavior, only then you can use MCS, else not. So MCS may be applied when a problem contains elements that exhibit a character of randomness. That is the first point to consider before going to MCS method. Now, some of the steps in MCS method, it is again first step, second step, and third step. The first step contains establish a probability distribution for each variable in the model. That's the important point. You have to establish a probability distribution for each variable you are working with in your model or planning to work with in a design with your model. That is subject to chance, subject to probability. So the second step is, so first step is basically to have idea about probability association with your random variable. Second thing, using random number, simulate values from the probability distribution for each variable. I will explain how you can do it. Using random number technique, simulate value from probability distribution for each variable in step 1. And the third step is repeat the process for series of repetitions, that is called runs, or you may call it trials. So this is the basic step. First step, you are generating or assigning probability for each random variable available. Second step, you are using and the simulative values you are generating from probability distribution assigned there. And third, you are developing and repeating and replicating the idea till you get the actual result. So why we want to simulate a variable, that a question now. I hope this question is being addressed now. For last 30 minutes, I was talking to this and probably I guess audience able to understand why we want to do the simulation, why we want to simulate a variable. More precisely, again I would repeat here that because there are many elements of uncertainties always prevail in a form of variable in measurement in nature. So many variables in real world system are probabilistic in nature, and since due to that reason we wish to simulate them. If the majority of the variables or events not have the characteristics and behavior of probabilistic characteristic, probably we do not require to do the simulation. Now, some of the very common practice where we are using simulation very frequently, because most of the people are aware with industry in around surrounding. So I say product demand, main product demand are uncertain. A shopkeeper don't know how many customers are coming today. A bank officer don't know how many customers are going to come between 12 a.m. to 12 p.m. to 1 p.m. So that is one thing, that product demand. If we don't know about that, simulation is the application area. Lead time for order placed. We have placed the order in inventory and we don't know, or we are not sure about lead time, that whether it come in 1 days with certainty or 2 days. Nobody can give guarantee because other factor may affect it, and that cannot be controlled. So the lead time for orders placed is another area where simulation in inventory management is have been used very frequently. Time between machine breakdown, another very frequent area where simulation is used. Time between machine breakdowns, that means if two machines has going and one machine breakdown, automatically the impact on other machine and productivity will be affected. So nobody will give a guarantee how much time it will get to repair, right? So immediately it cannot be done with a certainty that yes, within 2 minutes we are ready. Probably no. So again, simulation is being practiced there. Time between arrivals at a service facility, window center, or maybe in a bank or many more places, railway reservation, etc. That is simulation is one good idea. Service time, nobody is sure about service time. So that is totally unexpected. And therefore, to make it a better estimate of service time, we'll do the simulation very, very frequently. Time to complete a project activities. Again, simulation is very widely popular there. Number of employees absent from work on a given particular day. No office can say that today who is going to absent, because sometimes the absenteeism may be unplanned and maybe beyond control factor, and therefore it's not a guarantee that who is going to come definitely tomorrow. So that's why a number of employees absenteeism is being simulated almost every month in a big offices, so that the arrangement or the losses, possible losses due to unavailability of that particular employee could be addressed to. In a stock market performances, again the uncertainties are very high, and therefore simulation is being practiced in a particular as a routine task of share stocks business. Next level is some illustration. I'll take 5 minutes time to illustrate an example here so that you may able to understand how you do the simulation manually. In fact, machines are there today, but doing those machines, just doing programming without understanding this basis is really not going to help one. So there are many people who just learn programming. I have learned Python, I have learned this, I have learned this, but they don't know why you have learned it and what you will do after doing the programming, right? So that is the major question for the policies and the management that is coming as a challenge, because they want innovative mind. They don't want a mind of coding only, right? So here to illustrate how to establish probability distribution for a variable. First, I want to establish, let's generate probability. As I say, the first stage is to assign probability for each variable. So I'm giving you a stepwise illustration. Let's consider step one. Suppose we consider a monthly demand for some specific tire in a particular tire shop, right? Over the last 5 years, 60-month data is there, past data is there. So the data are shown in the on the next slide in a table form. And suppose this is the data. This is the data. Auto shared tire demand, and this is the demand per month, number of tires sold or number of tire demanded particular month. 300 tire 3 times, 320 last it is a history of last 5 years. That means during 60 months this is being happened. So 320 tires is being demanded 6 times, the frequency is 6. 340 tires 12 times. 360 tires has been demanded during last 5 years 18 times. 380 tires has been demanded during last 5 years 15 times, and 400 tires is being demanded during last 60 months 6 times. So total frequency capital N, you can say it capital N is 60. And then first of all I say we convert it frequency as a relative frequency to get the empirical probability. So it is 3 by 60, 6 by 60, 12 by 60, and so on. We get 6 by 60, and the probability value arrived here is 0.05, 0.10, 0.20, 0.30, 0.25, 0.10, or you may call it in terms of percentage. 5% of the demand come for 300 tire, 10% of demand come for 320 tires, 20% demand come for 340 tires, 30% come for 360, 25% come for 380, and 10% come for 400. So this is basically you have developed the first column. So you are given these two column only. Third column you have generated as a solution steps, right? So third column is generated deliberately. Why? Because we want to generate probability for demand. Now this will become our basis for further solution. That means we want to do the simulated demand. This is actual demand. I want to show you how you can generate a simulated demand without help of any computer programming. Later on, I will discuss some of the MS Excel and crystal ball approach or even R, but time will not permit us. So let's see. I'll try to make it more and more simple. So what is the next step? Next step, before moving to simulation, I just want to have an idea what is the based on past data, what is our expected demand. So what I say, if we assume that the past demand rate, because assumption is important, simulation is a modeling, and in every model there must be certain laws, assumption, restriction, etc., as I explained you earlier. So if we assume that the past demand rates will hold in future too, that is the assumption. If this assumption is violated, we can't do it simulation for this data. So we assume that the past demand of the tire will continue in future too. Under this assumption, we can convert this data to a probability distribution as I shown in the discussed in the table. And then step 2 will be simulate the values from probability distribution. But how we do that? So before doing the final simulation, we first compute the expected monthly demand. And that is the basic statistical formula. Expected X is equal to summation Xi Pi. We have each point and probability as we say in this previous table. So you can see this table. We have done 300 into 0.05 plus 320 into 0.10 and likewise plus 340 into 0.20. This calculation I have done here. So you can see it here. 300 into 0.05 plus 320 into 0.10 and so on. So we have multiplied, we have taken the sum of product of random variable with their respective probability, right? So the red color showing 358 tires. This 358 tires is basically simulated demand expected value? No, it is unsimulated value. It is based on the previous data. Now how you can find the simulated demand, right? So that I want to clear it. So far I have just find out expected demand of the tire based on last 60 month previous data. Now I will move to next step, further step. So make use of random number. Here is the role of random number. First time you have seen it. In a simulation, the role of random number is very, very important. And that's why you can say random number is basically one of the bases of simulation modeling. So you have to learn it, how to generate random number manually with a random number table, with a MS Excel, with a crystal ball software, with a R programming, with a Python programming, and so on and so forth. So here, make use of random number is a very first step required at this stage to simulate the demand. How do we do that now? How do we generate the random number? I am illustrating this step now, that we will now generate random number interval as shown below. So the next level is, you can see it here. The fourth column I have added it here now. So what I did, first of all, you have already demand and you have generated in the previous slide this probability 0.05, 0.10 relative probability for each demand based on previous record. After that, you generate the cumulative probability for each. So for 300 tire, the cumulative probability is 0.05. Then you add 0.05 with 0.10, it becomes 0.15. Then you add 0.20 and 0.15, it becomes 0.35 and so on. You keep on adding it. So finally 0.90, if you add 0.65 and 0.25, it becomes 0.90. And finally the total probability is 1. So cumulative probability is 1 here. and based on this, we will generate the random interval. So since it is 0 to 0.045, so I can take it, it will take or it will address a random number between 0, 1, 2, 3 and 4. So that's why I have given 0 to 4 as interval. Next interval I have frame is, so you can see it here, I consider n minus 1. So if it is 5, so I consider the upper boundary at n minus 5, n minus 1, that is 5 minus 1, 4. Similarly, 15, so 15 minus 1, 14. So next random number interval is from 5 to 14. And similarly, 35, 35 minus 1, 34. So next random number interval is 15 to 34 and so on, 35 to 64, 65 to 89, 90 to 99. And we have generated random number interval. The next level is very interesting. And here, that is called a step 4. Now what we do, we to simulate demand using number interval, we need to generate random number between 0 to 99. Why? Because it is 0 to 99. So we need a random number. How many random number you need? As many as possible. Suppose you want to generate 10-day simulation, 20-day simulation, you can do it, right? So for just for illustration, I have simulated only for 6 days. So consider, let's consider 6 different random number. I say you can use this random number directly from random number table, or you may use of the random number table, or you can use the computer like MS Excel, R programming. In R you can generate random number. In Python you can do it. In a crystal ball, at the risk, these are the inbuilt software especially designed for simulation. Simulink is another software that is also used for simulation. So you can use those software and generate random number. How many I have generated here? Just 6. You may generate 10. If you generate more and more random number, probably your simulation would be more and more accurate. So just for illustration, I have just generated 6 random number. And suppose I have taken the random number generated from R or Excel is 25, 39, 66, 76, 12 and 05. Then according to this, I am going to generate now the simulated demand. So let us see that if our random number is 25, you can check it. It's a 25, next is 39, next is 65, next is 76, next is 12, and next is 05. So when we look at this table, yes, here, this is your simulated demand. How it comes to? So go to the back table, right? The first random number generated is 25. So for 25, you can see where this 25 lie. 25 lie between 15 and 34. 25 lie between interval 15 and 34. Corresponding to this interval, what is the demand? 340. So your simulated demand for 25 is 340, right? Similarly, next random number is 39. 39 lie between 35 and 64. So corresponding demand is 360. So simulated demand for the random number 39, 39 is 360. And similarly, next random is 65. So for 65, this is here. And therefore simulated demand is 380 again. So you write 380. For 76, the 76 lie between 65 and 89. So simulated demand again 380. And then next number is 12. So 12 is here between 5 to 14. So simulated demand is 320. And the last random number was 5. It is your choice. You can do it 100 random number simulation, or you can generate as many as possible. The more randomization you do, the more simulation you do, the more accurate estimation you will get. So the last number is 5, random number, and 5 lie between 5 and 14, and therefore 320 is the lie. Same thing you have seen in this table. 340, 360, 380 twice, again come 320 and 320. So this is, I have illustrated in a how you can generate simulated demand from any given example for any given past data if you know little information, first of all you generated probability, then you generated cumulative probability, then you take in or generate a random number using any devices, and based on that random number and interval, that means this random number interval and random number, you are in a position to simulate the demand. So if you do it, now you can expect it. So what I say, this is the actual demand and this is your simulated demand. But if you do the simulation as large as possible, your actual demand and simulated demand average will going to be the same. And that is the beauty of your decision making using simulation. So the more simulation, more accuracy. So if you want to take a decision, that's why you need a 10,000 simulation, 1 lakh simulation, 10 lakh simulation. Can it be manually possible? No, it is taking a lot of time. And therefore the role of computer in simulation has been grown very fastly. Now, after finishing this illustration, I hope you're able to understand it. A few minutes I would like to highlight without going to depth. What are the statistical methods to generate random numbers? And I hope you must know it. Probably if not someone, then you must know it. Some of these statistical methods that is very commonly used for generating random number, one is called congruential method, another is called inverse transform method. If you Google out and you can find out, or you can go to references and research papers and you read it about this method, you can very easily do it. If time permits, I can illustrate it, and that's why I have not gone to depth of that, just mention it. Congruential method, inverse transformation method, acceptance rejection method, convolution method, modified acceptance rejection method, normal distribution method. These are the most popular among all other methods that can be programmed in a computer very easily, and with the support of computational devices, it is being done more and more frequently. So after this, the second last slide, where I would like to discuss how to do the simulation or generate random number in MS Excel, as well as there is another built-in software add-ins which is prevalent in MS Excel like MS Solver, that is called Crystal Wall. So first of all, I highlight Crystal Wall is an add-in tool available in MS Excel, right? In some version, you can check it there. Maybe that is a third-party system. So here I have given you left side what you want to simulate, from which what you want to simulate, and how is the formula and command. This will help you in doing it very simply. You can see CB means crystal ball. So if we want to generate continuous informed distribution between two number A and B, suppose I want to generate a continuous informed distribution, the random number from continuous informed distribution between 10 and 100, right? A and B, A is 10 and B is 100. We can simply type is equal to, in this CB dot inform A comma B. This is A comma B. Similarly, if you want to generate discrete informed distribution between A and B, that is for continuous, this is for discrete. Then CB dot discrete inform, that is very user friendly and command, just a common language command, discrete inform A comma B. And then similarly, you go to, suppose you want to generate a random number from normal distribution with mean mu and standard deviation sigma. These are the parameters of normal distribution. Then you can use CB means crystal ball, dot normal as a command, and then you can give a small bracket mu comma sigma. From exponential distribution for with mean rate mu, you can use CB dot exponential mu, and then for Poisson distribution with mean rate mu, you can use CB dot Poisson mu. From binomial distribution, if you want, you can use for normal with parameter n and p, you can use CB dot binomial pn. From triangular distribution with minimum value A, most likely value B, and maximum value C, that means ABC as a parameter of triangular distribution, you can use CB dot triangular A comma B comma C, right? So this is in crystal ball. Similarly, the another table is for MS Excel. I have left some of the function because it become lengthy, but these are commonly used. That's why I highlighted. If you want to generate random number using MS Excel built-in function, then first from the continuous informed distribution between A and B, you can use A plus B minus A multiplication sign star rand command, RAND rand, and then empty space. Argument, no argument required, blank argument. Then second part is discrete informed distribution between A and B. Just you can use rand between A and B, or without using rand between command, you can go to int bracket A plus B minus A plus 1 star rand command. Similarly, for normal distribution with parameter mu, you can use norm I and B. Then argument, first argument is rand, and second argument is mu, third argument is sigma. From exponential distribution with mean rate mu, you can use 1 upon mu a star ln. Ln is a command that is used for generating the exponential random number from exponential distribution. Then rand command. Then random number in general in MS Excel, if any cell you want, you can just type rand, and then you can without any argument into this. So rand command will generate a random number, right? If you want to just 100 random number, so it will give single value. If you just in Excel to that cell, take this value and click on the right corner, as many times as if you drag, so many random number with uniqueness will be generated. So rand command is very simple to use, very popular also. And then one more cases I have discussed. After that I will stop it. So discrete general distribution with two outcome A and B, probably with a probability of A, probability associated with outcome A is P. It is if rand less than P comma A comma B. And then the last discrete general distribution, that is for general distribution with more than two outcomes. We have to set a range, two range. One is range 1, where the cell range containing lower limit of random number, and another is range 2, where the cell range containing the variable values. And then we'll use the command that is called lookup command with argument rand, first argument as rand, second argument as range 1, this range 1 which you have defined it here, and then the second range is the value of this random variable, so range 2. If you use this, you will able to get it, generate it random number from this distribution. So finally I would like to say here, I would like to stop, and I would like to say thank you so much for your sincere participation and patience. Now you can ask related queries and doubts. I hope I would like to summarize. I have discussed few things. Number one, what is model? Number two, what is decision modeling? What are the steps of decision modeling? Why we do it? What are the merits and demerits of simulation? Meaning of simulation? Where do we can use simulations and why we can use simulations? The role of random number in simulations, Monte Carlo method of simulation. Then I have gone for decision modeling, probabilistic type and deterministic type. And finally, I have given one demonstration on MCM method to generate the simulative demand on a tire example. Many more things now you can do it. And lastly, I have illustrated the importance of illustrations of, you can do this table, I can make you for R also, for Python also, and you can learn it from there, that how you can simulate different random number methods using different software. There are so many software. Thank you so much. Once again, I stop it here. I open to the audience for question answer session now.
Yes, please. You may ask question.
Hello, sir. I am audible.
You have
Yes, please.
Yes, sir. Hello. Good evening, sir. I am Aman Raj, a first year undergrad at IIIT Bhagalpur. Want to ask you that for treatment of diseases like tumors and cancer, is simulation allow us to do nuclear experiment to check chances of curing the disease? And if this possible, which device is good for this purpose?
See, simulation is a mathematical methods. A particular device you cannot take it that is used. In fact, software, there are so many software that could be used if you have the proper input. For example, I have said that you can use Simulink, you can use Crystal Wall, you can use MS Excel add-ins features, you can use at the risk another software. So you can do simulation in Mathematica also, you can do simulation using MATLAB also, right? In a mini tab also the simulation option is there, SAS programming, Python program. So you can use the software and tools, subject to you should be well sure about variable, you should be well sure about your inputs, you should be well sure about correct information, processing of information, and then the steps which I discussed just now, that need to be followed first. So you can apply the simulation only when your variable have the behavior of randomness. That means each variable, measurable variable, must be associated with particular probability set. If it is not, you cannot do simulation on that basis. So simulation requires random variable of for which this certain deterministic probability is known to you. So that's why you have seen in the example what I did for a tire problem. I generate probability relative frequency approach, and then I can work on random interval, and then I develop the random, generate the random number, and then I illustrated the example. Oh, I hope, Aman, you understand it now.
Yes, sir. Thank you, sir.
Yes, anyone? Vishal, you
Any
were
other
asking.
students, please come up.
Yes, sir. Good
Yeah.
evening, sir.
Good evening.
Then Jem, you last. Yeah.
Sir, I want to ask how decision modeling is used in our artificial intelligence and data science system to make our healthcare system more efficient and more better.
In a healthcare system, let's take, I give one example. Let's take one example, and that would be more clear. Suppose most of the time what happens, a patient suffering from kidney failure realized at very last stage, right? And the level of creatinine measurement come only when in the mind of the patients, only when the troubles are very big, either the part of the kidney damaged or the full damage or one kidney damage or another survive, and that would be a dangerous condition, or if not dangerous, then very costly condition, a very later stage. So in what the normal practice today nowadays, that a common testing is recommended to that every person having the age 40 plus go for a routine task to have a normal records and measurement of their BP, their sugar, their other some common biometric measurements, indicators, and what you need to do, because it is not possible to do it every day, right? No patient have time, or no people have time to do all those things every day, especially at the age of 40, 50, because people are very busy. So what you do in a year, suppose you go for only 2 or 3 times measurement or testing of this data. Now these 3 events generated randomly from your body, measured through blood test or other recommended tests, you can simulate it 100 times or making just replicate it, because as you say, simulation is a replicated model. So simulate it 10,000 times and just get a expected value of count. I'm sure that there is no need to be worried, and that way most of the modern scientific medical sciences, they have simulation as a routine task in their healthcare treatment.
Yes.
Pandit, are you able to understand?
Yes, sir. Thank you, sir.
Right.
Jem, you were asking something? Ask one, sir.
Yes, sir. Sir, I understood simulation very well, but I have a one little doubt in modeling. In that type of modeling you mentioned, after like defining the problem, ki just develop the model. I want to know ki how the development of model is done.
Fine. Very good questions. See, when you define a problem, then what is the meaning of defining a problem? That you must know the outcome of the problem, input of the problems. So when you know the input variable, if for example, Suppose there is a econometric analysis and that expert want to read the current market condition due to Ukraine and Russian crisis. Since he is an economist by nature, he must know how the economic indicators like inflation is likely to be linked with other econometric parameters like international demand and supply of power sector, energy sector, petro sector, and related things. And based on that, they develop a particular variables, right? So set variables they incorporated. So very second step after defining the problem is a variable selection. Right variables should be selected in the model that require domain knowledge. A data scientist cannot do variable selection. Data scientists can facilitate the calculation part, computation part, idea part, modeling part. But that's why it is required a data scientist always work in a team. Whether it is in medical sciences, biomedical sciences, or clinical trials, or it is biotechnology or pure sciences and application in chemical and biomicrobiology. A team of people required. So domain expert people first decide about the variable. Second level, once the variable is well defined, parameter is well defined, then what is the functional relationship between variable and parameters? First, you should be sure. For example, I say people must know the relationship between F and acceleration generated and then mass of a body. Newtons have given this law. That's why a modeling and in a modeling process, as I said you, certain laws, certain axiom, certain rule, empirical knowledge must be there. Then only the functional relation will be developed. Once the functional relation developed between y and x, we are quite sure what that y is related to x linearly or non-linearly, exponentially. There is a relationship, logistic relationship, circular relationship, parabolic relationship, y square is equal to 4x kind of relationship, polynomial of any degree, because there are thousands of possibility of mathematical relationship. First, you make sure which kind of relationship exists between y and x and between the and how this parameter is linked with x in what way. Do we found any error term? That's why in regression modeling and others you have seen always there is a random error term. So that is the third stage. After that you can progress with solution part. Is it clear now?
Yes, sir. Thank you, sir.
Yes. Next question.
Is there anyone, please? No question? Okay. Please.
Student might get tired, sir.
Yes, sir. Actually, last session, that's why.
Right.
Thank you so much, Dr. Jiten Kumar, sir, for your precious time. Your respect
you, sir.
talk has
Thank you.
provided us with invaluable insights about decision modeling and simulation. You inform us how we can say that a formula or an equation is model or not. It's type deterministic and probabilistic, and steps involved that are formulation, solution, and implication. Then you talked about simulation and steps involved in it and about its advantage, disadvantage. You told us about the Monte Carlo simulation and the steps involved in it and application of simulation. You also showed an amazing example on simulation about demand of tire in an auto shop using probabilities and random number generation using statistical methods, ITM, ARM, etc. to simulate the demand, and also how simulation can be done in MS Excel and Crystal Ball. I am sure our participants have attained a better understanding about all these topics. Thank you again, sir, for taking out your valuable time to impart us with your knowledge. Thank you, sir.
Thank you. Thank you so much, sir. Thank you, audience. It's a pleasure experience to share with all, and looking forward to your further success. And I hope this STC is going to benefit a lot of students in many ways. That's because of rich resources of the teachers from different part of the country. Thank you so much. I wish all very best to all of you.
Thank you, sir.
Thank you so much, sir.
Okay, you all may leave it. Thank you, everyone. We will meet by tomorrow, same time, 1:55. No, 2 बजे resource person आ जाएंगे. By 2 they will join. So before 5 minutes, please join. Thank you. You all may leave it. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.